Education is the most powerful weapon which you can use to change the world.
Values with knowledge in students. Succeeding the paths of Sri Murri Lakshman Reddy, making education a positive experience. Sri Murri Rajashekhara Reddy, founder secretary, nurtured MLR group of institutions to win the pride of being recognized as one of engineering colleges in Telangana for consecutive academic years. Situated in vast and peaceful area of 35 acres, they tend to learn, experimenting their life projects through centers, which is tied up with industries, classrooms, corridors, advanced laboratories, equipped ultra-modern audio-visual technology auditorium, accommodating walk-ins, separate hostels for boys and girls. Each student is taken care for the provision of health facilities and hygienic food in spacious and eco-friendly canteen, etc. of large of institutions. AICE recognized MLR group of institutions accredited by NAC and has every accreditation for all programs. MLR Sports Complex and inaugurated by MLR group of institutions with most advanced multi-sports facilities like stadium, badminton court, tennis, billiards and basketball, etc. MLR Sports organizes many national and international university level sports fests, grooming every aspirant in competing national and international sports forums. Successfully achieved 50 gold medals, 13 silver medals and 16 bronze medals at in sports and opportunity creativity and entrepreneurial scaling platform for students' innovation and invention, which is loaded with ultra-modern equipments such as multimedia workstations, 3D printers, CNC machines, laser cutters, and thus provides stimulus for student entrepreneurs. The center has collaboration with various government and non-government ministries for raising seed fund to incubate student projects and startups. This center has developed 8 plus market-ready products and supported 11 plus student startups. MLR Group has set up livelihood business incubation in association with Ministry of Micro, Small and Medium Enterprise (MSME) to promote new technology or livelihood-based enterprises. Research and Development Cell has 12 centers of excellence in association with various industries and supports faculty and student research. It also has a track record of 25 plus funded projects, 700 plus SCI or Scopus Journal articles, and 35 plus intellectual property rights, and the progress continues. In preparing the aspirants to the real-world competitiveness, MLR Group of Institutions has introduced the Universal Corporation for Engineering Education (IUCW) to introduce outcome-based student-centric education and Bloom's taxonomy-based teaching, learning and evaluation process, engineering projects in association with Purdue University, USA. Scope: School of Programming Practices to hone the coding and programming skills. Students' platform for engineering education development. Speed: empowers the students to change in engineering education and its effect on society and environment. Club Literary to organize TEDx tech education skills to the global forum. MLR Library is fully loaded with diversified study material, books, national and international journals with dedicated digital library and online subscription to massive open online courses, IEEE, Elsevier, Springer, ACM journals, etc. MLR provides a safe and secure approach. Transport infrastructure includes modern and smart vehicles and strictly without the regulations with well-maintained safety standards. MLR Group of Institutions having faculty of nationwide professors include expert scientists of DRDO, DRDL, HAL, BHEL, SAE India, ECIL and JNTU. Imparts education with pure practical inputs. Offers courses in BTech, Aeronautical Engineering, Computer Science Engineering, Civil Engineering, Electronics and Communication Engineering, Electrical and Electronics Engineering, Information Technology, Mechanical Engineering, MTech with Aerospace Engineering, Computer Science Engineering, Embedded Systems, Digital Systems and Computer Electronics, CAD or CAM Engineering, Thermal Engineering, MBA courses. MLR proudly announces that till now 75% of their students have grabbed the opportunities with average salary package of 6 lakh by holding premier positions in top-notch companies in global market. MLR relies always on the philosophy that intelligence plus character. This is the goal of education.
Good morning, everyone. I am Nirmit Mishra, Assistant Professor in the Department of Aeronautical Engineering, and I welcome our today's speaker, Dr. L. Bhanuprakash-Garu, who has experience of 3 years as Associate Professor in MLR Institute of Technology. He has published 8 research papers and 3 H-index papers in the prestigious publications like elsewhere, and he has played a very key role in establishing Composite Lab in our college. I welcome you, sir, on this virtual platform.
Thank you, sir. Thank you, Nirmal, sir. I hope I am audible, sir.
Yes, sir, you're audible, sir. Okay. Yes, sir.
Yeah. Let me share my screen, sir. So is my screen visible?
Yes, sir, your screen is visible. We can view it.
Okay, so I can go ahead, right?
Yes, sir.
Yeah. So very warm welcome and very good morning to every participant. Myself, Dr. Bhanuprakash, and in today's session, I will be talking about multi-scale fiber reinforced nanocomposites, especially targeting at structural applications. So I hope in yesterday's talk by in the beginning talk, you might have already covered this composite materials, and their fabrication, different fabrication methods, and all. So I'll be taking you into the research aspects of these nanocomposites. So what are the possibilities that we have, and how many ways are present to undertake the research activities in this particular field, the composites, especially looking at the structural applications. Okay, so anyway, I'll go through. I'll give you the a brief introduction about the composite materials. I hope it won't be boring to you, or I hope it will be reinforcing your knowledge. Okay. So first of all, let me start with the definition, the fundamental definition. So what is a composite? How do we define it? So composites, it's a combination of, it is a material that is a combination of two or more dissimilar materials which are intimately bonded to form an integrated structure. So it is just a combination of two materials, we can say, but these are two dissimilar materials which are intimately bonded. It's a physical bonding only, and we do a physical bonding between these two materials, and we allow the material to form into an integrated structure. And this material, we can call it as a composite material. So here, if you see the characteristics of these composites, it will possess distinguishable interfaces between the constituents. Like whatever you have chosen the material, those two dissimilar material that you have picked up, so they will have distinct interfaces. Like you can clearly distinguish the interfaces between these two materials. I'll give you the example as well, and it will be more clearer in this aspect. And one more thing, by doing it so, by combining these two materials, we expect that the system will have superior properties than the individual component. Obviously, when it is, that's why we do the composite, we prepare the composites. So even though individually, if the material is not having that particular property, when it is combined with another material, so you can achieve that property, and so overall composite will have the superior properties than the individual components, we can say. So if I give you a microscopic image of fiber reinforced composite, so here you can clearly see that the binding material, that is a matrix. Okay, here the matrix is a polymer matrix. Okay, that is a binding material, and the reinforcement is a fiber. Fiber is clearly evident here, right? So this is a reinforcement, is a fiber material, and it is being binded with an continuous medium called as a matrix material, that is a polymer resin. So this is a microscopic image for the polymer composite system, fiber reinforced polymer composite system. Okay, where you can clearly distinguish the individual component, as I mentioned. So here polymer is being uh, used for binding up these fibers. So this is a reinforcement fiber, you can clearly notice in the microscope image. Okay, so that is what two dissimilar materials are combined to form an integrated structure, something like this. So here the catching point is, the what is the type of bonding that is involved here is a physical bonding. There will be no chemical bonds that are being present in this system. So we know that chemical bonds are stronger when it is compared with the physical bonding. In most of the cases in the composite material, we can only expect the physical bonding between the materials, and wherever chemical bonding is possible and is realized in the system, so that system will have, definitely will have very superior properties, or a greater amount of increment in the properties can be expected. So if I look at the roles of these matrix as well as reinforcement, matrix serves the following functions. First of all, it takes the load, whatever load that is being applied on the composite, so that will be taken by the matrix, and it eventually it will be transferring that load to the reinforcement material, where reinforcement is a principal load carrying element. Okay, the majority of the load is carried by the reinforcement fibers, and matrix just transfers the load that is being acted on it and to the reinforcement system. And also matrix does the binding of these reinforcement fibers, and it holds all the fibers into a desired positions, and also it protects the fibers from the environmental damages, like hazardous environment, or it is a physical abrasion, or any kind of environmental disturbances that is likely to be happen on the reinforcement. So this matrix will act as a barrier to it. Okay, and reinforcement is the ultimate load carrying element in the system. So in my talk, you can observe I'm more specifically talking about the fiber reinforced composites, and so the definitions also will be towards the fiber reinforced composite system. It is slightly different when it is compared with the other type of composite systems like metal matrix composites and ceramic composites. So definitions are slightly deviated and their roles also slightly deviated. So in my talk, I'll be more emphasizing on the fiber reinforced composites, which are extensively being used in the aerospace applications. And we are talking about their structural applications. So structural composites is nothing but the composite system which takes the load. So whatever the load bearing composites we can say, that is a structural composite system. So I can give you the best example, that is deployable military bridges. So these military people, if they find any obstacle like any river that is being that they have to cross, so what they do is these kind of foldable bridges which are being carried over the heavy trucks, so that will be deployed at the location, and eventually they will be passing through, all the vehicles, military vehicles will be passing over these bridges. So such kind of bridge should have definitely it should have a lightweight, and also it should be very stronger enough to withhold the weights of all these military vehicles, right? So always there is a possibility that always there are so many research opportunities to develop the material which are having lighter in weight, and which are very stronger in its nature. So composites will give you, to some extent or the greater extent, composites will gives the solutions for these kind of applications. So yeah, that's why we use the composites. So what is the beauty of these composites? The beauty of these composites is its weight saving potential. So these composites are having very light in weight, so they always, and there is no compromise on the strength. If I give you example, CFR base, that is a carbon fiber reinforced plastics. So carbon fiber reinforced polymer composites will have strength. It is 5 times stronger than the steel, 1020 grade steel. It's a 5 times the strength of the steel. And when you look at the weight aspects, so it is comparable with the aluminum weight. We know that aluminum is having very light in its weight, right? So where CFRP composites are having very lightweight, which is comparable to the aluminum, and in the strength aspects, it is 5 times stronger than the steel material, 1020 grade steel material, right? Similarly, if I look at compare the properties with respect to aluminum itself, so it is having 2 times the modulus of aluminum and also 7 times stronger than the aluminum material. So that is the beauty of these composite materials. Okay, so it is having a very greater weight saving potential in its engineering applications. So if I move on, now you know that composites is a combination of 2 or more materials, and you know that the weight, it is having greater weight saving potential, and it can be used for the structural applications. So when exactly you can think of using these composites? We cannot derive these composites into each and every engineering material. We cannot replace all the engineering materials with a composite system because there are many other aspects that we have to consider. I'll come into that. So when exactly you should think of using these composites? If I say a few things which are very critical, so one parameter that is very critical in your application, that is if it is weight reduction. Weight reduction is very critical in your engineering application. Then you can think of using these composites. So in which area, particularly in which area this weight reduction will be a critical parameter is the aerospace sector, and also the space applications, right? So here this helps in reducing the fuel consumption, and so that it will increase the range in its transport or increases the acceleration to your vehicle, right? And in the civilian structural applications as well, the building that you're seeing here, that is developed by the IIT Madras research team, where there is no concrete, is nowhere the concrete is being used, not for the foundation, not for the walls, side walls. Everything is made out of glass fiber reinforced gypsum panels. So they have the plan to fabricate these glass fiber reinforced gypsum panels. Gypsum is the binding material for the glass fiber. Glass fibers are the reinforcement, and gypsum is the industrial waste. We all know that. So from the industrial waste material, they have prepared these structural panels, and these structural panels are being used for constructing these building. The main advantage that we can get is these panels are ready-made. So at the industry, you can fabricate it in a very quick interval. And also, if you're making up any concrete-based structures, so you have to work greater on the digging activities. The foundation activities are heavy, depending on the structure, right? Depending on the number of floors and all. So here, that much of severe digging and severe foundation works are not required because it's light in weight materials. Um, yeah. So even today, this building is there. If you're happen to visit IIT Madras, I'll recommend to visit this building as well. And this is the one area where weight reduction is very critical. Then you can think of using composites. And another one where you're looking at durability of your material and also maintenance free. So durability is very critical when you have applications in the marine sector. So marine, the problem with the marine sector is salt water. So if you use any metal, is so mostly it happens to get rusted. If it is iron based ferrous alloy, definitely it is likely to be rusted. And also its weight is very heavy. You will need to reduce the weight as well as you need to have more durability. And what we do is we paint the system regularly in the regular intervals. We do the maintenance. So maintenance cost is also will become critical here. If you use in that area, if you replace the metals with the composites, so it will composites do not rust. That is one advantage. And also they have the excellent fatigue resistance. These are maintenance free, so your maintenance is also very minimal. So in that area, these composites are, we can use this composite materials. And another area where you're looking at added functionality or multi-functionality to your system. So one that example I can give you is radar applications like the stealth aircrafts. So if you want your aircraft that is invisible, as well as your structure and all other aspects need to be uh, very strong as well as lightweight, then in such applications you can think of using these composite materials that absorbs the radar signals. You can incorporate such kind of materials in the composites, and so you will get the invisibility, radar invisibility. And if you're looking at any thermal insulation, that is also achievable, and electrical insulation also can be achievable in this particular system. So such kind of added functionality you can give it to your system. And if you're looking at multifunctionality, then obviously you can go with the composite materials. And last but not the least, that is a design freedom. So we will have the architectural freedom. So you can design your strength. You can design the strength in a particular direction. So if you want stronger tensile properties in particular direction, so you can orient your fibers in that particular direction, and you can achieve that. So if you clearly know the dynamics of your system, and so you can have the freedom to architect your material. So that is a beauty of these composites. And also many components can be consolidated into one component. So in the metal system, so we do the welding, we join the materials with the nut and bolts. So such kind of many components you can consolidate into single component, and so you will get more structural integrity as well as strength to your component. So these are the areas where in your application, if you find it, these are the critical parameters. So you can think of using these composite materials. So am I teaching you something a new topic? I don't think so. These composites. There are many in the nature. Uh, there are many in the nature. So if you find, if I tell you a few examples, so the best one is wood. Wood, it's a composite system. So wood is a combination of lignin and cellulose material. So lignin and cellulose combinedly forming into the wood. So this can be called as an composite system. And our bones are also, we can say that is a composite system where bone cells are combined with the calcium-based minerals. So they will be getting integrated. We will be seeing an integrated structure which is having a good strength. So bones are basically made out of bone cells and calcium-based minerals. Altogether, these are a composite system. And in fact, our human body itself, we can call it as a composite system where human body is made out of tissues and bones. So these tissues and bones, they just have the physical bonding or binding, but not the chemical bonding. Okay, so we can call our human body itself, it's a composite system. So what we are doing by observing our nature, so we are trying to mimic it into the engineering applications. We are trying to imitate into all kind of engineering sectors, starting with the construction, transportation, marine, aerospace, energy, virtually all sectors of engineering, we are imitating these composite materials. Two examples I would like to give you. So one is a recent aerospace vehicle, that is a Boeing 787. So Boeing 787, the website itself, they will be clearly mentioning that 50% of the material that they have used is advanced composites. So half of its material that is being used with a fiber reinforced composites. So depending on the area, so wherever the mechanical properties are dominant, so depending on it, whether it is tensile property or the compression or any toughness need to be very high. So accordingly, we will be selecting different type of fibers and we'll be uh, adding. But however, altogether, advanced composites are going at 50%. So half of the materials that are being used will be coming out of composite system, and 20% is coming from aluminum, and 15% is titanium, and 10% is the steel, especially the landing gear applications over there. And remaining plastics and other areas, we'll be finding 5% of remaining material. And we know that Simon is the leading manufacturers for the wind blades, and these wind blades are made up of fiber reinforced composite materials. Yeah, moving ahead, I'll quickly give you the classification of the composite. We know it's a composite. We can define composite is it's a combination of matrix and reinforcement. So based on the matrix, we can classify the composites, as well as based on the reinforcement, we can classify the composites. So one is based on the matrix, we can classify as organic matrix composites, metal matrix composites, and ceramic matrix composites. And under the organic matrix composites, again, polymer matrix composites and carbon matrix composites. So common metal matrix composites, that includes aluminum as a continuous medium, or the titanium, magnesium, copper alloys, everything can be used as the matrix. And into this matrix material, we'll be adding reinforcement material. So the matrix properties will be further improved by adding the additional materials called reinforcements. Similarly, the ceramic matrix, where oxides and nitrides or carbides are being considered. So aluminum oxide, silicon nitride, or any carbides, we can pick it. So, and then if you see the polymer composites, so we know that, yeah, before that, we see the based on the reinforcement, we can classify as particulate composites. That is, if the reinforcement is of 0 dimensions, so that is a particles. If you use the particles as a reinforcement, then those composites, we can call it as a particulate composites. If you use one-dimensional materials, that is a fibers. So fiber reinforced composites, we can call them. If you use the reinforcement form, in its two-dimensional form, that is a sheet form. So such kind of composites we call it as a laminar composites. So if you pick polymer composites, so we know that polymers are two categories exactly. So that is thermoset polymers as well as the thermoplastic polymers. So we know the differences. One is a recyclable, non-recyclable. So in general, in our structural applications, thermosets have been considered for the engineering applications because of their low shrinkage and also their good mechanical properties. So yeah, and well, coming to the fiber reinforced composites, so in most of the cases for the structural applications, continuous fiber is being used, whether it may be unidirectional one or bidirectional one or three-directional one. So, so if it is glass fibers, so these are glass fibers, sheets or the mat you can see. Carbon fibers will look something like this. It's a two-dimensional or the bidirectional carbon fibers. So carbon fibers have been oriented in two directions, which are perpendicular to each other. So if it is a unidirectional, so all the fibers will be oriented in one particular direction. There is no fiber that is coming in the opposite direction, that is at 90 degrees. And we have other system where the discontinuous fibers. So discontinuous fibers are called as a chopped fiber. So all these chopped fibers are stacked into one layer sort of thing. So then we can call it as it's a mat, chopped strand mat. So these chopped strand mats, it is expected that they will have the homogeneous properties, but not for the continuous system. So continuous system, depending on the direction of the fiber, the properties of the fiber will be changing. So if all the fibers are oriented in maybe one particular direction, X or Y, so in the direction of the fiber, the properties of the fiber will be very high, but not on the transverse direction. So that depends on which type of fiber we'll be using. So that depends on your end application. We have to pick the material. And if you see the fabrication of composites, so we have both conventional methods as well as advanced methods. So in the conventional methods, I can say we have the contact molding or the press molding. So under the contact molding, a very old technique and easy technique that is called as a hand layup technique. So where we'll be just laying up the fibers, and then each fiber, when you lay up each fiber, so that will be poured with the resin or the matrix polymer material, and we'll be rolling it and forming it into the shape of your mold. So chosen mold. So it is very simple process, hand layup technique, and spray up is just an automated fabrication method to the hand layup technique. So where the resin and fiber both will be sent through a pressurized channel. So there is a pipe that is sending the pressurized resin, and there is a scissoring system as well. So where these toes of fiber toes will be chopped using the chopping gun. So this chopped fibers along with the resin that will be sprayed onto the mold surfaces. So according to your desired thickness, so we'll be applying this resin fiber system. So we'll get the end component. And the last one, that is a press molding. So we have the female and male components, molds. So in between we'll be placing the your polymer resin along with the fiber system, so combinedly. So we'll be just applying the pressure, and we eventually will be getting the end products. So advantages out of these conventional methods, we have the easy processing. So the steps that are being adopted in this is very simple and straightforward, and we don't require any trained professional for getting the components out of these methods. And these are low cost tooling. There's no tooling is required. Heavy tooling is not required. So all whatever we are using is a low cost tooling. So these are the advantages that we can get, but there are many limitations as well. Mainly laminates tend to be resin rich. There is no control on the resin that we are applying. So resin, we know that resin is nothing but the polymer matrix. So we know that ultimate load carrying element in the fiber reinforced composites is a reinforcement fibers, right? Load carrying element in composites is a reinforcement fibers. So, and the matrix is just a binding material. So, and it is a weak in its properties. So this binding material shouldn't be very high. So if you give more amount of binding material and apply the load, this binding material will fail first before it is before it is effectively transfers its load to the reinforcement fiber. So before it is transferring also, it takes the greater amount, and then it fails first before the fibers. So what we have to do is we have to restrict the amount of the resin. So we have to use the binding material, how much it is required, only that much we need to supply into the composite, so that we'll get good properties to your end laminate. So that kind of control we may not be having if you use the conventional techniques like hand lab, spray up, and press molding. And always these composites are tend to have voids, because we will be just pouring the resin and then spreading it. So when you are laying up one fiber over the other fiber, so you may find air gaps that is being trapped between the fibers, and there is no method to eliminate these gaps that are being stuck in between the fibers. So you don't have control on the voids, number of voids that is going to be coming in your laminate. So these are the limitations, and so these techniques will not be used for any structural applications, but rather if it is but even we will be seeing most of the boat hulls are made up of this simple hand lap technique. Even a 75-meter big boat hull can be made out of this hand lap technique. Even today people are being adopting this technique because of its simplicity, and where the voids is not a critical parameter. You can restrict the number of voids if you are trained enough, and you can limit the resin as well. And if you go with the advanced techniques, we have two. I'm going to talk about two advanced techniques. One is a vacuum assisted resin transfer molding. Other one is a resin film infusion process. So in the vacuum assisted resin transfer molding, as the name itself suggests, it is the resin transfer. Resin will be transferred here. So we, according to our desired thickness, we stack the fiber, and then we seal the material. This is a vacuum seal. So and then what we do is we do the two pipings and two ends of these fiber mats. So at the one of this passage will be linked to the resin, that is a polymer matrix, and other one is to the vacuum pump. So we create a pressure gradient between these between one end of the fiber to the other end of the fiber. And so if this passage is open to the atmospheric pressure, then here this end will be at the negative pressure, that is a vacuum pressure. So pressure gradient will be created, and because of this pressure gradient, resin will be transferred from one end to the other end. So it is basically a vacuum driven resin transfer molding process. So during this process, whatever air that is being trapped between the fibers, everything will be pushed to the other end point, because smoothly all the resin will be coming from one end to the other end. So wherever, if at all any air is present, so that will be taken care by this vacuum hose. Okay, so once the transfer is done, we leave the components for reacting and solidifying it. So eventually, and then we will be removing all this bagging materials. So here we have very much control on the resin, first of all. So only a limited amount of resin will be transferred here. And also we will be, since it is the bag is completely sealed and it is under a pressure, negative pressure. So you will have very good compaction for your laminates. And the tooling cost, we don't be using heavy tooling here. We don't require a heavy equipment as well. So cost of this fabrication method is relatively cheaper. And we have very good control on the resin, the amount of resin as well as the voids. So void and resin, content of the resin, we have greater control, and the end laminates will be very good. So both the large component parts as well as the small components can be manufactured here. A simple oven is required for curing this polymer resin. And when it comes to the resin film infusion process, so as the name suggests here, resin films have to be manufactured here. So in all the cases, whatever we have discussed, we are considering the liquid resin, right? In this resin film infusion, this polymer resin are made into films, just like the fiber mats. These resin films will be fabricated using calendering process. When the polymer is brought between the two rollers and pushed, so just like sheet metal processing, how we do the same way, resin films will be fabricated initially, and these and then these fabric and resin film sandwiches are considered according to your desired thickness, and these sandwiches are covered with the bagging material and everything, and it is vacuum driven, vacuum sealed when it is put it into the uh, oven. So first these films will melt, and then so localized flow can be observed here. So this localized flow that wets the fibers, and we will have an excellent control on the resin that is being present between the fibers. We'll have greater control on this, on the resin part. So, and we will be having very low void fractions, less than 0.5 percentage, and we can see the greater compaction, and so the properties will be very good. So this is a calendering equipment, so where we can prepare this polymer films, resin films. Okay, so these are the two advanced methods using which we can fabricate fiber reinforced composites. Yeah, coming to the nano composites. So far I haven't included anywhere, I haven't included the nanoparticles. So we were just talking about matrix and reinforcement. Okay, just the polymer matrix and fiber reinforcement. So now I would like to fabricate nano composites. Okay, so how do I fabricate it? So how do I introduce my nanofillers into the system? So whether I can incorporate in the matrix, that is a liquid polymer, or whether I can directly bring it onto the reinforcement fibers. So as I mentioned, so composite is a combination of matrix and reinforcement. So here you can introduce the nanofillers in two different ways. One, you can introduce it introduce it into the matrix system, that is polymer, the liquid polymer. Directly you can add these nanofiller powder into the polymer resin, or you can coat this nanofillers onto the reinforcement fabric system. So in these two ways, you can introduce the nanofillers into the composites, and you can fabricate the nano composites. Okay, so but what are the major challenges? So if I go through the literature survey, and if I mention you the challenges that are present in these two cases, the first one, the interfacial adhesion between nanofillers and matrix. You will be just dropping the reinforcement particles, that is a nanofillers, into your polymer resin, right? But there should be some kind of adhesion, interfacial adhesion should be there between the nanofillers and matrix. Then only you will have connection between this matrix and reinforcement, matrix and nanofillers, right? So when this interfacial adhesion, or when this connection is not there between the nanofiller and the matrix, what happens is whatever load that is being applied on the composite, so first it is coming onto the matrix. So in the matrix, nanofillers will be dispersed, So if the load need to be transferred to the nanofiller, so if you want nanofillers also need to take the load, then there should be connection between this matrix molecules and nanofiller atoms. Okay, so if it is physical adhesion, or if you can generate chemical bonding between these two, then before it is transferred onto the reinforcement, before the load is transferred onto the reinforcement, some of the load will be taken care by this nanofillers itself, because we know the nanofillers will be having very good, excellent mechanical properties and other properties. So as these are also challenging materials for taking up the load, so some of the load will be taken care by this nanofiller when it is having very good adhesion. So how to develop this physical adhesion or interfacial adhesion or chemical bonding between these nanofillers and matrix, that is a one challenge, a greater challenge. And homogeneous dispersion of nanofillers in the matrix. So if you just drop your nanofiller powder onto the into their polymer matrix, and if you just mix it for a while, so you will not generate homogeneous dispersion. Rather, these nanofillers will be forming as an agglomerate. So all the nanofillers will come at one location, and they will be uh, they will form into a cluster or aggregates, or we can say agglomeration. That's the right word, is agglomeration. So agglomeration is what we can see, what is straight away we can expect from the nanofillers, because nanofillers, because of their dimensionality, they will have very high surface energy. We know that when high surface energy is there for any material, it tries to reduce, right? That's why in the winter season, we try to fold ourselves and reduce the surface area, so that we will be less likely to get affected by the cold, right? The same way, nanofillers also, because they have very high surface energy, so they try to reduce its surface energy by joining with the adjacent material, right? So all the nanofillers will come at one location and forms into an agglomeration. So when you have that kind of agglomerates, you will be eventually losing its nano dimensional properties, because those agglomerates will come into micro scale, and where you will not see any difference in its properties. So the critical challenge is getting the homogeneous dispersion. So one is the interfacial adhesion, other one is a homogeneous dispersion. These two are very critical. These are the challenges when you directly add the nanofillers into the polymer system. And if you want to coat the nanofillers, example here I can show you is these are the CNTs, carbon nanotubes, that are dispersed in the epoxy resin. So they are separated in one another. There is no agglomeration here. So it is nicely dispersed, homogeneously dispersed, I can say, in the matrix system. So if the same thing, if I want to achieve it on the reinforcement fiber also. So if you see this particular image, so you can see all the nanotubes, carbon nanotubes, they are nicely coated on the fiber surfaces. Okay, these are carbon nanotubes coated onto the glass fiber surfaces. So when you are doing it, so the challenge will be, if you want to generate this kind of coating, so the challenge will be controlled production of nanofillers coated reinforcement fibers. So the production of these coated fibers is it's a challenge, first of all. And even if you do it at the lab level, but if you want to bring it onto the industrial scale, where you have to prepare these coated fibers at a tons of lengths, and then scaled into industrial production, it's very critical and it's very challenging. So these are the two fundamental challenges that we can see in this coated reinforcement fibers. However, there are some techniques. All these researchers are working on it, and I'll talk about few of the cases in both the ways. If I talk about, first, let me talk about matrix modified matrix being modified with the nanofillers. There are number of routes. I'll talk about them. So you can add your nanofillers directly into the organic solvent. So like you have your polymer material. Eventually, you have to get it polymer matrix that is being modified with the nanofillers. So we know that polymer matrix will be having viscous in its nature. So it's just like honey kind of viscosity will be there. So when the viscous medium into the viscous medium, again these nanofillers are nothing but the solid particles. If you add the solid particles into the viscous medium, again its viscosity will be increasing, and so you will not get a good dispersion or the distribution. Okay, that will become very critical. So in order to, so for that, one method is, if you want to get it in that way directly, if you want to disperse it, one method is you have to use this high shear mixing equipment. So this high shear mixing equipment, you have to use it. So where you'll be using a planetary blade system, and that it will be mixing it. You need to mix it. High shear mixing need to be done for at least 2 or 3 days. Then only you will get good dispersion of nanofillers in the polymer. So if you want to, if it is very difficult, what we can do is first we will disperse these nanofillers into the any organic solvent. So any organic solvent, starting with the acetone, methanol, ethanol, toluene, dichloromethane, and then chloroform or tetrahydrofuran, then dimethyl formamide, any of the organic solvent we can pick it. And so first you will be preparing the dispersions in the organic solvent, because organic solvent's viscosity is comparable with the water, like water. So just like water, organic solvent will be there, the viscosity. So you can easily disperse the nanofillers in the organic solvent. So, and then you add this, once you achieve good dispersion in the organic solvent, that solution we need to add it into the polymer. And we have to again stir it. So here mechanical stirring need to be adopted. Okay, mechanical stirring need to be done for at least 24 hours. 24 hours stirring is required. Then eventually you will be getting dispersion in the polymer matrix itself. But we don't want this organic solvent. What we do is we heat the system during your mechanical stirring process. We heat the suspension to the melting temperature, boiling temperatures of organic solvent. So when you heat it to the boiling temperatures, then all this organic solvent will be vaporized, so that in your end component, end system, you will not have any organic solvent, traces of any organic solvents. So your dispersion will come in only polymer, and nanofillers will be there. That is a direct dispersion method. That is a one way where you'll be using mechanical stirring and ultrasonication for dispersing the nanofillers in the organic solvent. Then we have polymers. In the polymers, directly we can do it. So we can either use organic solvent plus nanomer. Directly we can do it in the polymers. If you want to directly do it in the polymers, we need to go with the high shear mixing process. Or there is another method where we can use the surfactants. This is called the functionalization method. I'll talk more about it. And other medium, like other coupling agents, we can say all these are coupling agents, we can say. So other dispersion aids can be your DNA or protein or starch will become the coupling agent between your nanofiller and the polymer. So these are the three different ways. So another thing, that is a chemical functionalization you can use. Chemical functionalization is nothing but you will be modifying the nanofiller surfaces with the active functional groups, and these functional groups will link with your polymer. So let us say polymer will be binded with, if I pick epoxy resin, so it requires amine based hardener. resin and hardener is there. So resin is your polymer system, and hardener will be your amine-based solution. Amine-based means NH2 groups will be there. So if these NH2 groups are being generated on the nanofillers, that is on the nanotubes here, so these NH2 groups will bind with the polymer, and that is how a chemical bonding can be introduced between the polymer and nanofillers. And if you do that, if you achieve this chemical bonding, so whatever load that is being acted on the matrix, that will be effectively transferred onto the nanofillers, and eventually the properties of the material will be increasing. So functionalization we can classify into two types. One is a covalent functionalization, other one is a non-covalent. Nothing but if you introduce covalent bonds between the functional group and the nanofiller. So here it is a direct and indirect method. So one is indirect, is wherever defect region is there, you will be attacking over there. So direct side wall is you will be attacking onto the regular atomic structure. Okay, modifying the regular atomic structure. So non-covalent way is the surfactant. As the name itself it is says. So what this surfactant will do is, if it is a particle, it will be just capping the entire material. Okay, if the nanofiller is a particle, let us say here it is a fiber. So if it is a fiber, so whatever surfactant that you choose, that will be wrapping onto the fiber surfaces. So if it is completely wrapped up onto the fiber surfaces, it will be isolated from adjacent nanofiller. In that way, you will get you will avoid the problem of agglomeration, and eventually you will have the homogeneous distribution, and so the properties will be improved. So these are the two ways you can modify this chemical functionalization using directly modifying the fiber surfaces, the nanofiller surfaces, or you can use the surfactants to have a bonding between the matrix and nanofillers. So these are the different routes for modifying the matrix. And if you see the reinforcement modification methods, so reinforcement modification with nanofillers, and then what are the different routes are there. So first one, directly we can grow the nanofillers onto the fiber surfaces. So anyway, during your production itself, production of nanofillers itself, so whatever you produce nanofillers, so directly you produce this nanofiller onto the fiber surfaces. So in that regard, what they do is, so carbon nanotubes will be generated on a particular substrate. So substrate will be coated with some metal oxides. So this metal oxide will act as a precursor material, and over that metal oxide particles, so these nanotubes will be growing. So in the CVD, chemical vapor deposition process. So instead of using a substrate, a regular substrate, what they do is they will use this fiber, your fiber, as a substrate. So onto this fiber, first a metal oxide will be coated here onto these fiber surfaces, and wherever metal oxide is present, so that will be the route for growing this carbon nanotubes. So like that, directly you can grow the CNTs onto the fiber surfaces, and that's how you can introduce nanofillers onto the reinforcement fibers. Second one, we have the electrophoretic deposition. So electrophoretic deposition of CNTs onto the fiber surfaces. So electrophoretic deposition is nothing but it is similar to the electrolysis process, where charged ions will be uh, moved onto the electrodes, right? Deposited onto the electrodes. So here also, but here we will be using charged particles. Charged particles will be dispersed in the any solution, whether it can be organic solvent or it can be water also. So first, if you're talking about nanocomposites, nanotubes will be introduced into the water solution or the ethanol solution, and they will be nicely dispersed. Then we will be taking two electrodes. So in front of any one of the electrode where these charged particles will be depositing. So we'll be just placing these fibers in front of any electrodes. if it is a glass fiber. If it is a carbon fiber, we know it is a conducting fiber, so that directly it can be used as an electrode. So charged particles will be getting deposited onto the electrodes. So that is a electrophoretic deposition technique. That is how we can coat the fibers. Third one, we have CNT is disposed in polymer blend that is used as a sizing. Okay, so we know that all the fibers will be treated with some kind of sizing agents. So when you're applying the sizing during its manufacturing process itself, so that sizing material will be dispersed with the CNT blended polymers. So it will be having some kind of charge. So this carbon fibers, the sizing will be created with the anionic charge, and if you are coated with the cationic, so both anion and cation will bind together, and that's how you will have adhesion of these fibers. You can coat the fiber surfaces with the nanotubes. That is another route. And the simple technique that I can illustrate here is a dip coating of fiber surfaces in the carbon additive disposal solution. So what we do is we prepare nanofiller solution, and then simply we can dip the fiber into it and leave it for some time, so that charged particles will get deposited onto these fiber surfaces, and we will just take out and then wash it thoroughly, and whichever remains, that will be remained forever. So this is a simple dip coating process. So dip coating is you can industrialize this process, but direct growth of CNTs, it is very much restricted at the lab level experiments. It is very difficult to produce directly grow the nanotubes onto the fiber surfaces, that too at the very large lengths. That is very difficult. It cannot be industrialized. Electrophoretic deposition, to some extent we can think of industrializing it, and CNT blended polymer, CNT disposed polymer blends, this also can be industrialized. And to large extent, this dip coating of fiber surfaces, this method can be industrialized here. So these are the different techniques that so far people have come across to modify the fiber surface or to introduce the nanofillers onto the reinforcement fibers. So I think somebody is doing annotation. Can Nirmit sir or Sweta madam, can you restrict the participants to?
Yes, sir.
Yeah. So I'll talk about my work, what I've done. So I have mostly worked on graphene-based composite system. So I have worked with both the carbon nanotubes as well as graphene. I have been worked on. So carbon nanotubes is my MTech thesis, master's thesis, where I have whatever images that you have seen previously for the fibers of modified fiber surfaces as well as the modified matrix images. So that was from my master's work. And during my doctoral thesis, I have worked on the graphene-based composites. So both in the matrix modified system as well as the reinforcement modified system I have been working on. So graphene is having different derivatives. So the pure graphene as well as oxide form and exfoliated form and all. So in each and every case I have been explored. So my work has been divided into the three categories. First, I have worked it at the nano composite level, so where nanofillers are directly introduced into the epoxy resin, and I have studied the mechanical properties. From this work, I could comment on, I could know that what is the concentrations of nanofiller that I can add, what are the maximum concentrations, and what is the optimum uh, range of nanofillers at which I can expect some improvement in the properties that I can come across, or if at all it is giving whether I can notice any improvement in the properties or not, also I can come to know. So from this beginning work, that is a nanocomposite level work, so I have derived those, I have received some challenging results, and with that I have went ahead and modified the fiber reinforced composite system. So for modifying the nanofillers, for introducing, first I have tried with the introduction of nanofillers in the matrix composites, in the matrix system. Then I have introduced nanofillers onto the surfaces of reinforcement fabric. So here I have used the direct dispersion methods, and in the reinforcement modification system, I have used electrophoretic deposition. So as the name itself indicate, as the figures or microscopic images illustrates here. So yeah, nanofillers are being considered in the matrix system. So if I zoom it and show you, yeah. So graphene is it's a two-dimensional nanofiller. So you can see all these are modified nanofillers. Graphene is present in the matrix material. This is a fiber and this is a matrix. So these will be the nanofillers. Nanofillers are nanosheets, graphene sheet. These are the graphene sheet. So this is a microscopic image for the matrix modified system. So let me briefly take you to my work. So the nanocomposite level, what we have done is first we have prepared different forms of graphite derivatives, as I mentioned, in the oxide form, exfoliated form, and then the reduction form, different forms of different derivatives of graphites we have first prepared at the lab level. We haven't directly purchased it. We have prepared in the lab itself. Then we have characterized. So for each and every stage, for confirming the oxidation reaction, for confirming the exfoliation process, for confirming the reduction process. So we have to characterize the nanofillers. We have characterized under XRD, X-ray diffraction, FTIR, Fourier transform infrared spectrum, and then FESEM, so field emission scanning electron microscopic images. So from these three techniques, we have confirmed the oxidation followed by the exfoliation and reduction processes. Then we have adopted the method for generating the nanocomposites. We have prepared it and characterized for tensile, compression, and flexural. And we have studied their fracture surfaces and to evaluate the dispersion of the nanofillers in the system, as well as the fracture, the kind of fracture that is being involved in the specimens. So first oxidation is being followed through modified Hammer's method. Hammer is the first person who has done the, in 1956 he has done the oxidation of graphite using three oxidizing agents. One is sodium nitrate, and then the sulfuric acid and potassium permanganate, KMnO4. Using these three strong oxidizers, graphite is being oxidized, and then graphite oxide will be generated. So in the down the line, so people have been optimized this Hammer's method, and the advanced, the latest optimized technique is being adopted for my work. And then from the graphite oxides, so we have thermal exfoliated the graphite oxide in two ways: by suddenly heating it at 200 degrees centigrade and gradually heating up to 450 degrees centigrade. In two ways we have exfoliated it, and then finally we have chemically reduced it to bring it into graphene shape, graphene nanoparticles. So we have finally reduced it using a strong reducing agent, that is hydrazine hydrate. Okay, so these are the FESM images. So this is a graphite flakes. So this is my starting material. So you can see I can just magnify up to 3K. So even at 3K, I can clearly see the flakes, graphite flakes here. But when it is oxidized, you can see these graphite flakes will have at least 1,000 to maybe at least 600 to 800 stack of graphene sheets will be stacked, and then we can call that as a graphene. Graphite is nothing but a stack of graphene layers. Graphene is a single layer of carbon atoms. Hexagonal array, hexagonal network of carbon atoms, single layer is called as a graphene. So such single layers are being stacked into. So if it is stacked for 500 to 800 graphene sheets, we can say that as a graphite. Okay. So when you're doing oxidation process, these stacking of graphene sheets will be broken because of the acid treatment, sulfuric acid and other strong oxidizing agents. These sheets will be broken, and oxygen groups will be introduced between these graphene sheets. Oxygen groups like hydroxyl groups and all that. So this is a SEM image for the graphite oxides. So you can clearly see the stacking is being reduced. I mean, the size of the graphene is being reduced here, and so the magnification also. We have to go further deep to analyze the component. So that is 10K magnification. Here it is 3K magnification. And then we have exfoliated uh, at 200 degrees centigrade. Suddenly this graphite oxide is being uh, brought into the 200 degrees centigrade. So because of that sudden change, so what happens is all these graphene sheets, these oxides, whatever present, so that will be removing. As a result of that, it will be exerting some kind of pressure between the sheets. As a result of that, the sheets are being expanded. You can see many expanded sheets. So if you consider this is a stack of 100 sheets, maybe, or less than that. So in each and every case, this is a single graphene sheet. I can say this is a single graphene sheet. So each and every graphene sheet is pushed away, pushed a bit because of the pressure that is being exerted. However, wherever it is possible, it is being broken also, and so the size of the graphene sheet here, exfoliated graphite oxide, is further reduced. So in the previous case, graphite oxide case, it is observed at 10K magnification, but now to observe this exfoliated graphite oxide, I have to further deep down. So to 30K magnification, I have to use. And similarly, exfoliation at 450 also resulted into the similar structure, but we cannot see sudden expansion because this is gradually being heated to 450 degrees centigrade. It's not the sudden change, thermal gradient. It's not a thermal, it's not a sudden change in the, it's not a sudden heating. And so eventually these particles, these sheets are being crumpled on the surfaces, can be noticed here. When it is being reduced using reduction technique, right, using the strong reducing agent like hydrogen hydrate, so all the oxygen groups are being removed here. As a result of that, stacks, these sheets are further broken into very few number of sheets, like 5 to 8 sheets are combined, or maybe sometimes a single sheet also can be noticed. Here you can see beautiful transparent graphene sheet can be noticed here. Even in the folding, the edges are being folded, and here I can clearly notice my graphene flakes, right? So when the reduction is happened further, you have been brought down, so the material size will be reducing. So I have to look at 60K 60,000 magnification. I have to do it in order to capture the filler. So it indicates that there is a breakdown is happening from the graphite. Graphite is 500 to 800 graphene sheets are been stacked. When it is oxidation is done, when it is treated with the acids, it is broken into maybe half or so, and further it is been, when it is exfoliated, again it is been broken down, and when it is comes to reduction process, finally it is somewhere around less than 5 number of graphene sheets. Some in some area we can pick one single sheet also, one single graphene sheet also can be evident. So these are the different derivatives. All these different derivatives are being observed for nanocomposites. So which one is good for my, for increasing the properties? So that is what my study is. We have done the XRD spectra to confirm the oxidation followed by the reduction processes. Upon the oxidation, I could notice a peak crystallographic changes can be noticed here. The peak has been shifted upon the oxidation. So when the exfoliation is done, so again this oxygen groups have been removed. That is a very evident. Again, it is coming back to its graphite peak. Similarly, at the reduction process as well. The functional groups, what are the functional groups that are present that can be confirmed from the FTIR spectra? So upon the oxidation, all these carboxyl group, carbonyl groups, and then hydroxyl groups, all these are observed under this FTIR spectra. And when they are being exfoliated and the reduction has been done, so all these groups are removed, and peaks are slowly, they are they are disappeared. That has been clearly observed here. So, and I have followed the solvent assisted ultrasonication method here. So I have used organic solvent. First, I have dispersed nanofillers into different organic solvents like acetone, chloroform, DMF, methanol, methyl ethyl ketone, and tetrahydrofuran. Six different organic solvents into it. I have prepared the graphene dispersions. I have observed it for 24 hours, and after 24 hours, so with solution in acetone, the graphene has been settled down, and chloroform to some extent is okay, and DMF is giving a very good dispersion even after 24 hours. The nanofillers are not settled down, and methanol and methyl ethyl ketone is also settled down the particles, and THF is also giving good dispersion. So DMF and THF is my conclusion. I can go either of these organic solvents, but DMF is having boiling very high boiling point when it is compared to the THF, where THF is it's only up to 70 degrees centigrade or 65 degrees centigrade boiling point. So easily I can remove this THF. So I have picked this THF as my organic solvent, and first I have dispersed all the nanofillers in the THF, and that solution is eventually transferred into the uh, epoxy resin. Epoxy is my matrix material, polymer matrix here. So first graphite oxide is being added to the THF, and we have sonicated using ultrasonic probe. Once the uniform dispersion has been achieved, so that is being this solution is being added to this solution. Epoxy resin is being added. Again, I have dispersed this using sonication. So afterwards, once the sonication is achieved, I have to remove the organic solvent. So during that, both the mechanical stirring as well as under hot plate. So hot plate that is set at 70 degrees centigrade. So the solution will become at 70 degrees centigrade. At this point of time, organic solvent will be evaporated. So eventually we get epoxy. Epoxy and nanofiller dispersion. So once you get this epoxy and nanofiller dispersion, we will pour it into the mold surfaces, into the mold to generate the tensile test specimens. For tensile specimens, we have the dovetail specimen, something like this. I mean, this is a mold. We just pour it and then cure it. And for the compression test, you need to prepare the cylindrical specimen. And for the flexural bending samples, you need to prepare a rectangular specimen. So in each and every case, we have different molds. And as prepared, epoxy resin system is being poured into different cases, and composite specimens are being prepared. And it is being tested for all these properties, flexural strength, bending strength, and all. So we have noticed a good improvement, or it's a good sign at the nano composite level. We have noticed improvement with the reduced reduced exfoliated graphite oxide, REGO and EGO exfoliated case. The 10% improvement is being noticed. And then in the compression also, we have noticed up to 15% improvement with the exfoliated graphite oxide. And there is no effect on the tensile properties. That is evident, because tensile property, if you want to improve any tensile property, so you always require covalent bonds between the fillers, so between the filler and matrix material. So if there is no covalent bond, so when the material is being pulled, so under tensile loading, so these reinforcement, the load will not be transferred onto the nanofiller. So nanofiller will not be participating under this tensile load. So wherever nanofiller is there, it lacks like a stress concentration region only. So eventually it will either the properties will reduce or it will remain as the same. So we didn't expected any improvement in this tensile property here. And we have seen the fracture surface images, and we could notice at one weight percentage of nanofiller combination, so we can see very high amount of agglomerations. When it is at the low concentration, so it is, you can see very nice homogeneous dispersions are being observed. When it is one weight percentage, this kind of clumsy or clusters of nanofillers are being agglomerated nanofillers are being observed. So we have not in further experiments, we have not used 1 weight percentage. So we have restricted our experiments less than 0.5 weight percentage. Then moved on, we have fabricated fiber reinforced composites using vacuum bagging technique. Using vacuum bagging technique, we have prepared the composites. So these are the vacuum bagging components. So and then we have studied under flexural studies according to the ASTM standards. We have prepared the samples, cut into the desired shapes. These are the laminates and cut into the desired shapes, that is rectangular shapes. And we have tested under 3-point bend fixture. And according to the ASTM standards, we have calculated both the flexural strength as well as the modulus, and we could notice very good improvement in the fiber reinforced composite level, up to 44% improvement we could notice here in the strength, and also the modulus was also improved. And similarly, interlaminar shear strength is also is been tested, and it is a very critical study, we can say. If this interlaminar shear will indicate the bonding strength between the fiber and the matrix. So that is also improved with the presence of nanofillers. Nanofillers have promoted the bonding or the binding between matrix and reinforcement, where we could notice 48% improvement with RAGOKs at very, very low concentration, that is that is at 0.258%. Similarly, we have done very interesting studies here. Mode 1 fracture studies. Mode 1 and mode 2 we have done. So mode 1 is an opening mode fracture, just like the tensile mode fracture. So first we have introduced a film pre-crack. This is nothing but the pre-crack. So wherever this film is there, so there will be no bonding between the fibers. So this can be treated as a pre-crack. So up to this region, there is a pre-crack. So freely the sample will open up. So at this point, at the end of this, at the tip of this film, so the bonding, it need to overcome the bond strength. So that is a fracture toughness, we can say, the resistance offered against the crack propagation. So crack initiation as well as the crack propagation, both things have been covered. So as per the ASTM D7, D5528, we have followed this test. So we can notice this has been captured using a camera, 8MP camera. So and then further video have been split into the number of frames, and we have clearly studied the propagation of the crack using image software. Each and every frame has been clearly observed with crack propagation, and we have drawn the graph between crack propagation and crack initiation. Both the initiation fracture toughness and propagation fracture toughness has been calculated. And here also we have observed a very good improvement in the properties. So at 0.5 we can notice 65% improvement. At 0.25 it is 48% improvement. Propagation is higher further, but in the most of the cases, initiation is considered to be the fracture toughness. So that is also very good, very high, we have observed. And the extension, that is a delamination length, that is a crack length to the mode fracture toughness is being drawn here. This is a baseline, and very good improvement can be noticed with a reduced EGOKs. And these are the fracture surface images that are being studied. So if the baseline composite without any nanofiller, the fiber surfaces will look something like this. It's very smooth, and there is no matrix that is being stuck on the fiber surfaces. But however, when nanofillers are present in the matrix material, you can see some of the polymer along with the nanofiller, it has been bonded on the fiber surfaces. So they are having very strong adhesion between the fiber surfaces and the polymer matrix in the case of GO. And however, we have observed very good strength with respect to the RAGO, where it is clearly observed in the fracture surfaces also. The binding between the resin and that is a polymer and the fiber is very, very tight here. See, all the fiber surfaces are having matrix material along with the along with your nano fillers, right? So these are all nano fillers. They are tightly binded here. So this is what promoting the strength. This is what causing the improvement in the properties. And similarly, the mode 2 fracture, it is a shear fracture, we can say. So it is tested under the flexural conditions, 3-point bending load condition. So we have seen the similar way we have tested it, and we have noticed a very good improvement as well. The nanofiller dispersion has been studied. Also, the fiber surfaces here also you can see. These are the clean fiber surfaces in the baseline composite without nanofillers. Fiber surfaces are very clean. And you see with the GO as well as REGO, see how the fibers are being tightly wrapped up with the matrix material because of the presence of nanofillers. See the layer of matrix that has been tightly adhered onto the fibers. So that is how the physical bonding is being improved with the presence of nanofillers. And yeah, and this work is being published in Polymer Composites, and it is already received more than 10 citations. And the next one, I have modified the reinforcement fiber systems with the nanofiller. So in this regard, I have studied with the carbon fiber system. So since I have considered electrophoretic deposition as a method I have chosen for modifying the reinforcement. So in that regard, I require electrodes which are conducting. So I have chosen carbon fibers as my conducting electrodes. So this is the setup here. So you will be having a DC power supply, and you have the two electrodes. Between that, your fiber will be there. So in both the cases, and between this positive and negative electrode, so that is a negative electrode is a cathode, and anode. Anode is your fiber. So at the both the sides of the fiber, that is the nanofillers are being coated. Okay, so the charged particles will be deposited onto the anode electrode. That is anode electrode. Here it is the carbon fiber. So if I use only one electrode, so one of the side only getting coated, so other side will become plain. So on the both sides I have used cathode electrodes. So in the both sides, my carbon fiber is deposited with the nanofillers. So here the EPD parameters are 4 parameters I could notice here. First one is the separation between the electrodes. That is one of the parameter, that is between the electrodes, so separation, the distance. We have fixed it to 1 centimeter, that is a 10 mm for both the cases. And other one is a voltage applied. So based on the voltage applied also, the deposition rate will be increasing, or deposition thickness as well as deposition rate will be increasing or decreasing. So that is another parameter. And time, how long you will be supplying the charge. So the time was also a critical parameter for your thickness of the deposition, and the nanofiller concentration in the solution. So based on the concentration also, your deposition will be decreasing or increasing. So two parameters I have fixed it. One is a separation between the electrodes, that is a 10 mm has been fixed, and nanofiller concentration is also fixed with 0.25 mg per ml. So Arjun has raised hand. So let me finish my talk and then I'll answer your question. Is that fine? I hope that will be all right. So nanofiller concentration also I have fixed it at 0.25 mg per ml. Then first I have optimized this voltage that is need to be required and time that I have to follow. So I have tried with the different combinations like 20 volts and 10 minutes, and 20 volts and 20 minutes, 40 volts and 10 minutes, and different cases. And I have analyzed under microscopic images for the thickness, and I have chosen 20 volts and 20 minutes is giving me the uniform deposition, and so I have followed this, and I have fixed these two parameters as well. And I have coated with a GO and REGO, two cases here. EGO I have eliminated. So graphene oxide and reduced graphene oxide, reduced exfoliated graphene oxide has been considered for the experiments. So first I have deposited in the same way. Then the first test I have done is a contact angle measurement. So this is an indication for your surface roughness. It is expected that when nanofillers are present on the surface, your surface roughness will be increasing. If the surface roughness is increasing, and you have to observe a reduction in the contact angle. So we have done the experiments, and we have also confirmed it, the reduction in the contact angle. So if it is uncoated carbon fibers that is having contact angle of 38 degrees, whereas graphene oxide coated carbon fibers are at 28 degree, and RAGO reduced graphene oxide one, which is having 30-degree contact angle. So there is a reduction in contact angle that has been observed. If the reduction is there, that is from the surface roughness will be increasing, and so it is having very good wetting with respect to the polymer matrix. So if you improve the wetting, so it is you can improve the physical adhesion between the matrix and reinforcement. So first we have confirmed that, and then we have here we have just increased. We have so to in order to do the multiple coatings as a simultaneous in single shot. So we have scaled up our fabrication setup. First, we have calculated how many plies are required, and then we have prepared the solutions, as well as accordingly we have prepared the scaled up the devices as well. Here we have followed the vacuum assisted resin transfer molding directly. So resin is being driven from one end to the other end point, and we have tested for the flexural strength. We have noticed very good improvement to 25%, and we have tested with the ILSS. ILSS has been significantly improved up to 45%. We could notice, and then interlaminar shear. Yeah, mode-on fracture we have done. So mode-on fracture also increased by 15%. So in each and every case, we have noticed very good improvement, but the fracture is slightly different here because matrix is plain here. It is not a matrix modified one, but fiber is being modified here. So you can see the crack that is being developed on the epoxy. This is a plain epoxy, so you can see the step kind of cracking. If it is filled with a nanofiller, a different kind of failure you can expect. But wherever fiber surfaces are there, on the fiber surfaces, matrix is tightly bonded. You can see with the RAGO coated carbon fibers, so very good adhesion. And in this particular case also, matrix has been tightly adhered with the fiber surfaces. So that is very clear here from the fracture surfaces. And then we have studied the electrical conductivity. We know that graphene is having very good electrical conductivity. So we expected further this conductivity could improve. So, and this is very critical for the aerospace applications because the outer surfaces of your aeroplane that need to be conducting because it need to if it is non-conducting when it is lightening, so that will be concentrated at one particular area, and then eventually it will be end up in failure of the structure. So what they do is in general, so they take a continuous conducting medium. So conducting wire or a strip will be introduced on its structure, so that whichever lightning comes, and this will become a conducting medium, and so that will be transferred eventually onto the ground. So if you're improving the conductivity of your composite materials itself, the outer casing itself, you can eliminate that that electrical strip as so. So in that applications, in that regard, we have studied the electrical conductivity measurements we have done. So where we could notice through thickness properties have been improved by 127%. Through thickness means it will be having a layer of polymer fiber, that is through the thickness dimensions. And in plane direction, in plane obviously carbon fiber will be there, and that is very good conducting itself. And so we have noticed a minimal improvement, that is a 15% improvement. And this work is published in Computer Science and Technology elsewhere, and it's already received more than 16 citations have been received so far. The last year itself, it has been this work has been published. So we have plenty of opportunities in this particular area. So the way how you modify the fiber surfaces, or the way you treat your matrix material, so you can come up with the different combinations. Okay, yeah. So that's it from my end. So I'm open for the question and answers, if anything is there. Hello.
So any questions from the participants, you can please type in the chat window, or you can unmute yourself.
Good morning, sir.
Yeah, good morning, sir.
Sir, is there any difference between HVOF and plasma spray, sir? To quote on carbon composites.
Okay, if it is carbon composites, both will be the matrix and reinforcement will be carbon based material only. So what was your question exactly?
Sir, actually I want to study ablation studies, sir.
Abrasion, okay.
Yes, ablation.
Ablation,
So I
ablation,
want
okay, sorry.
ceramic particles on the CC composites.
Okay.
To improve the ablation resistance enhancement.
Okay.
So for that purpose, I want to go for. Actually, I went to CVI, but the CVI process is somewhat complicated, and it takes more time.
Okay.
So that I moved to coating, sir. Plasma spray and high velocity oxy fuels.
Okay.
Can I coat by using those processes?
I haven't worked in that area, to be precise. I may not be the right person to answer. I cannot say a negative thing. So I'm not aware of it. These plasma coatings and all. I haven't done with the plasma thing, but simple chemical functionalization techniques I have been aware of it. Where the chemistry need to be.
Can I coat on CC composites? Can I coat ceramic composites, ceramic particles?
Yes, we can do. Ceramic particles also we can do. It's a you need to. Ceramic is okay. We can do actually. It's a wherever the ceramic particles, can you functionalize it? The carbides and oxides only. So
yes,
if you can break any one of the groups, so you will be introducing the dangling bonds. So when free bonds are there, then obviously they will try to bind with the reinforcement fibers.
Okay, sir.
I hope you can do that. Somehow you find a way to introduce a charge onto the particles.
Yes.
And that will become the means for your deposition, your coating.
Okay, sir.
Yeah.
Thank you, sir.
Yeah, thank you.
Any more questions?
In the chat box, anything is there now?
Okay.
There's only one question regarding feedback, ma'am, in the chat box.
Yes, I changed it.
Okay.
So thank you very much, sir, for your time and your valuable information with us.
Thank you, everyone. I hope it is informative. something you could extract it from here, I
And
think.
also, I thank the participants. I thank the participants for taking time, and they are just attending even in this busy schedule.
Yeah, thank you everyone. If anything is there, you can get my contact details with Sweta ma'am. So, or I'll drop it in the chat room, so you can ping me at any time. And we do offer some kind of consultancy services from our laboratory. We do have the stir casting facility for doing the metal matrix composites, for fabricating metal matrix composites for aluminum based and magnesium based. And we have also set up for polymer composites as well. Where we can do vacuum assisted resin transfer molding technique. If this FDB is conducted offline, definitely we were offering an hands-on experience as well. Unfortunately, our pandemic time is uh, made us to go with the online session. So if any consultancy services are required, so you can contact us through our HOD at the department, aeronautical as well as the mechanical department. I'll drop my contact details here, so you can ask me. Yeah, I hope that will do, ma'am. Yeah. So my mobile number and mail ID is being dropped here, so in the chat room. Yeah. If anything is there, let us know. You can drop me either WhatsApp or that is the one that is my WhatsApp number as well. So we are very happy to serve you.
Any consultancy or research projects, you can always contact Dr. Bhanuprakash sir, Aeronautical HOD Dr. Gupta, or Mechanical HOD Venkateshwar Reddy sir. The details are available in our website mlrinstitutions.ac.in. Even if you miss the uh, contact details right now, you can always log on to mlrinstitutions.ac.in. So thank you very much for the session, sir. So with this, we come to the end of the session. And on behalf of Aeronautical Department and the staff, the team of the department and the participants, I wholeheartedly thank you for your valuable time.
Sure, ma'am. Thank you.
Yeah.
Thanks a lot, ma'am. Yeah, for giving this
Thank
opportunity
you
and
very much.
interacting with the
Yeah.
participants.
No, it's very difficult with this computer, talking to a computer.
Yeah. So thank you, everyone. Thank you, ma'am. So yeah, I can leave the session, right?
Yes, sir.
So thank you.
So the afternoon session we are having with Dr. Manas Das. He is from IIT Guwahati, and his topic will be magnetic field assisted finishing of aerospace materials using smart magnetorheological fluid. Magnetic field assisted finishing of aerospace materials using smart magnetorheological fluid, and it would be an interesting session. Uh, Please log in by 1:50 p.m. Sir would start the session at 2 o'clock. Till 3:30, you will be having the session. The link is the same. So we'll break for lunch now. Thank you very much, sir.
Thank you.
The feedback form is given. You can please fill the feedback form and you can leave the session and join in the afternoon session.